In this section, we explain how to calculate the reaction forces. When an action force with a horizontal component acts on a cantilever beam, a cantilever beam is a statically determinate structure with 3 reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in 3 directions. For an object at rest, equilibrium in all directions must be satisfied. The cantilever beam, we will discuss, has a free end at point A, a fixed support at point B, and a length of L. As shown in the figure, we will determine the reaction forces caused by the action force P with the horizontal component on the cantilever beam, also shown in the figure. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. Step 1. Create a free body diagram of the reaction forces. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely in the horizontal and rotational directions, but restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. The free end, at point A, allows for movement in all directions, so there are no reaction forces acting in any direction. The fixed support, at point B, restrains vertical, horizontal, and rotational movements of the beam, so the reaction forces at point B are the vertical reaction force VB, which restrains vertical movement, the horizontal reaction force HB, which restrains horizontal movement, and the reaction moment MB, which restrains rotational movement. The directions of the reaction forces are assumed as follows. VB is upward, HB is leftward, and MB is clockwise, as shown in the figure. Note that the symbol for the reaction moment shown in the free body diagram uses the same notation, M, as the action moment. Therefore, it is necessary to analyze whether the M symbol in the free body diagram represents the action moment or the reaction moment, and to proceed with the analysis of force equilibrium and other related analyses accordingly. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. First, decompose the action force P into its vertical and horizontal components. Create the rectangle, with the action force P, as the diagonal. The directions of the two orthogonal sides of the rectangle should be aligned with the directions of the reaction forces, namely the vertical and horizontal directions. From the sides of this rectangle, the magnitude of the vertical component of the action force P is the square root of 3 divided by 2 multiplied by P. And its direction is downward. The magnitude of the horizontal component is the 1/2 of P. And its direction is rightward. Since we are dealing with forces, always verify both the magnitude and direction. Additionally, for the 3 components of a force, be sure to check the point of application as well. The unit of a moment is not Newton, but Newton meter. Therefore, the momentum cannot be summed with the translational forces with the unit of Newton. A moment is a quantity that does not need to be considered in the equilibrium of translational forces. In other words, a moment does not affect translational motion, but only affects its rotational motion. We will now analyze the equilibrium of forces in the vertical direction. Refer to the free body diagram of the reaction forces for the vertical forces. The vertical forces are the square root of 3 divided by 2 multiplied by P at point A, and VB at point B. We will derive the equilibrium equation for these forces. In the vertical force summation, forces acting upward are considered positive. Let's clarify this. The force, the square root of 3 divided by 2, multiplied by P, acts downward, so it contributes, minus the square root of 3 divided by 2, multiplied by P. The force VB acts upward, so it contributes, plus VB. To achieve equilibrium of these vertical forces, the algebraic sum must be 0. This concludes the discussion on vertical forces. We will now analyze the equilibrium of forces in the horizontal direction. Refer to the free body diagram of the reaction forces for the horizontal forces. The horizontal forces are the 1/2 of P at point A and HB at point B. We will derive the equilibrium equation for these forces. In the horizontal force summation, forces acting rightward are considered positive. Let's clarify this. The force the 1/2 of P acts rightward, so it contributes, plus the 1/2 of P. The force HB acts leftward, so it contributes, minus HB. To achieve equilibrium of these horizontal forces, the algebraic sum must be 0. This concludes the discussion on horizontal forces. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action, for the square root of 3 divided by 2, multiplied by p. The line of action for the 1/2 of p. The line of action, for Vb. The line of action, for Hb, is the same as the line of action, for the 1/2 of p. To determine the magnitude and direction of the moment caused by a translational force, it is necessary to have information about the arm length relative to the center of rotation, which is calculated from the force's line of action. In contrast, the reaction moment mb in the figure already has the defined magnitude of mb and the clockwise direction. Therefore, the concepts of line of action and arm length are not necessary for the moment. Next, select the center of rotation. Choosing the point through which as many lines of action of the unknown reaction forces pass as possible will simplify the calculations for determining these reaction forces. In this case, we will select point B, through which the lines of action of the unknown forces Vb and Hb pass as the center of rotation. Then, calculate the shortest distance from each line of action to the center of rotation at point B. This shortest distance will serve as the moment arm length for each force relative to the center of rotation. The arm length for the force the square root of 3 divided by 2 multiplied by p is L. Since the line of action of the force, the 1/2 of p, passes through point B, the arm length is 0. Similarly, the line of action of the force, Vb, also passes through point B, so its arm length is 0. For the force Hb, since its line of action also passes through point B, the arm length is 0. We will derive the equilibrium equation for these moments. In the summation of moments, clockwise moments are considered positive. The center of rotation is point B. Let's clarify this. The action force, the square root of 3 divided by 2, multiplied by p, acts counterclockwise, so it contributes, minus the square root of 3 divided by 2, multiplied by p, and multiplied by L. Since the arm length of the 1/2 of p, with respect to the center of rotation, is 0, its contribution is 0. Similarly, the arm length of Vb, with respect to the center of rotation, is 0, its contribution is 0. The arm length of Hb, with respect to the center of rotation, is also 0, its contribution is 0. The reaction moment mb acts clockwise, so it contributes plus mb. To achieve equilibrium of moments, the algebraic sum must be 0. This concludes the discussion on rotational equilibrium. The reaction forces, Vb, Hb, and mb, are determined through the equilibrium of forces in 3 directions as follows. The signs of these forces are based on the free body diagram, shown on the left. The positive sign of Vb indicates that this reaction force acts upward, which is consistent with the vector, assumed in the free body diagram. The positive sign of HB indicates that this reaction force acts leftward, which is consistent with the vector, assumed in the free body diagram. The positive sign of MB indicates that this reaction moment acts clockwise, which is consistent with the vector, assumed in the free body diagram.